Bismillah ar-Rahman ar-Rahim. Alhamdulillah, sallallahu alaihi wasallam. This is a lecture. Basically, it's a complementary lecture to what we've done in the class over the past three classes, where I'm going to go over a review. It's basically a review to all what we've done, and with an additional examples and additional illustrations of what we've done in the class. So let's start. We are doing capacitance and dielectrics, and basically what we'll be looking at, we wanted to examine what a capacitor is and what's a capacitance of a capacitor. So it's مكثف and السعة. And then after that we want to look at what happens if you introduce a dielectric material and put it in between the plates of the capacitor. Okay, so and obviously what we wanted to do, the objective is to understand what these devices are and how are they, or what the function or what the purpose of these devices or what they're used for. And I think everybody knows that the capacitor is used to store electrostatic energy. So there are different types of capacitors that we see in everyday life, starting from this old variable tuning capacitor to all of these fancy new ones, which some of them are very, very tiny, and these old ceramic disc and the ceramic adjustable and so forth. So we've seen these, and as I said, the purpose of these devices, electronic devices, is basically to store energy. And one of the there are many applications for capacitors in our daily life, and the easiest one that we experience every day is the capacitor used to in the camera for the flashlight. So the charge or the energy is stored in the capacitor, and when you click your camera, the charge is the capacitor is discharged in such a way that you get that very quick flashlight, which helps you take the picture. So let's start in order to explain what capacitors are and how do they work and what is going on, and also we wanted to relate it to what we've taken before or so far. So the best way of understanding this is to simply relate it to gravitational, or go back to gravitational potential energy and understand what potential energy is really like, or what it is. So if you remember, we had anywhere near the surface of the earth, so this is the surface of the earth, and if you have a mass and that mass is allowed to move or drop, then it's going to move from point A to point B, and point A being the point of high potential, and point B being the point of low potential, and the force acting on this is mg, which is the force due to gravity. So if you look at the potential energy, which is defined as the work done by the gravitational attraction, and we've worked this in physics 1 in such a way that work due to or done by gravity is equal to F dotted with D, and F is the force or the weight, and D is the distance between the 2 points, H final minus H initial, and cosine theta is the angle between the force and D in this case, which is 0. And we see that we have seen, because H final is smaller than HF, so this will be negative, and then we see that the work done as detailed in physics 1 is equal to the change in potential energy. Let's move to electrostatics. So in electrostatics, what we have a parallel plate capacitor. The easiest one to see, and we can visualize, easy to visualize, is the parallel plate capacitor, where you have a plate, the positive plate is said to be the high potential or the point of high potential, and the negative plate is said to be the point of low potential. If you allow a positive charge to move inside this uniform field, and which produces a force that is equal to Fq, then the charge will move from a high potential to, or the point of high potential A, to a point of low potential B. So in a parallel plate capacitor, the point of high potential is the positive and the low potential is the negative, and E will be applied, of course, if the force is simply Q, the charge, multiplied by the electron. If it is a proton where it's positive, then it will move along the direction of the electric field lines, and hence it will move from high potential to low potential. However, if it is an electron, it will do the opposite. It will move from a point of low potential to a point of high potential. And from here, you can easily, equivalent to here, you can easily calculate the potential difference, the electric potential difference, delta V, which is simply VA minus VB, and it's ED1 minus ED2, and if we take this to be S, then the potential difference is delta V is equal to the electric field multiplied by the distance between them, S, so that the charge travels through a change in electric potential. This is very important. So if you allow a charge, if a charge experiences a difference, a potential difference, then it will move. However, if there is no potential difference between the 2 points, then the charge is not expected to move, and thus it will not experience any work. So very quickly again, to carry on, in potential energy we have the gravitational potential energy, we have mgh, and if we go to the electrostatic potential energy, so m will be q, and the gravitational field will be the electrostatic field, and the potential energy, the electrostatic potential, or the change in the work, is equal to F multiplied by D, and F is simply equal to QE. And of course, if I want the potential V, which is simply W, or the work over Q, then that will be ED, and therefore we have delta V is equal to ED. This is the very famous formula. So the change in electric potential is defined as the electric field multiplied by D, and D is the distance traveled by the charge. So let's say if you have an electron that goes from the positive plate all the way to the negative plate, then if it starts from here and then it goes all the way down, then the electrostatic potential energy is simply QV, and then from there you can get, if you divide by Q, then you get the V, and V is simply ED, as we've seen here. Now that's the same, you can use the same analogy in the gravitational field. This is an exercise that we've done in class, and it's simply just to illustrate the points that I've done a few minutes ago. And don't forget the concept of zero potential. No, remember, in gravitational potential energy, we set, and I again emphasize the point, set the zero potential to be at the surface of the earth. So that's my reference point. For electrostatic potential, we chose, or actually not chose, but we found out that the potential energy, or the potential, is actually zero only at zero at infinity. When r goes to infinity, 1 over infinity is equal to 0, and that's what the concept of zero potential is. Okay, now let's move on to our topic. So we just reminded ourselves of what happens when I have an electric field, a uniform electric field, and a charge will move along the electric field only if it experiences a potential difference, which is defined as E multiplied by D. So a capacitor, as everybody knows, is simply a passive electronic device that is used to store energy. And it's the capacitor is simply two plates which are parallel to each other, and I think the best one, the famous one that we're familiar with, is the parallel plate capacitor, where we have two plates which have the same charge in magnitude but opposite in sign, and they're separated by some distance d, and if you're away from the edges, the electric field is uniform. So that's what comprises a capacitor, and it's the area. Each plate has an area E, and then, as I said, they're separated by a gap, what we call a gap, a D. Sometimes it's they're in between the plates. There is something called, we insert a material that is called a dielectric, and we'll see what that means later on in the lecture today. So the capacitance. Now, this is a capacitor. The capacitance of a capacitor is a constant value that is directly proportional to the surface area of the plates and inversely proportional to the separation between them, and also it's proportional to the medium epsilon naught, so characteristic of the medium epsilon naught. Now remember, capacitance, as we'll see in a minute, capacitance is a quantity that is a geometric. It depends on geometry only. It depends on the area and the gap in between, or the distance in between the plates and the medium between. There are three types of capacitors. We've just seen the parallel plate capacitor. There is also this cylindrical plate capacitor, or this cylindrical capacitor, in which I have a cylindrical shell, and then there is a gap, and then or inner cylindrical shell, and then there is an outer cylindrical shell. One of them is negatively charged, and one of this is a negatively charged, and this is positively charged. And remember, in a capacitor, the distance between any 2 points, so for example, the distance between these 2 points is the same, the distance between these 2 points, the same as these distance between 2 points, so the gap is constant throughout. And the electric field is uniform within the at any point here. So if you take this point, the electric field is the same as this point, the same electric field, this one, and so forth. And then we have the spherical plate capacitor, where you have two spherical shells. Now remember, these guys are concentric; they share the same center. Similarly here, they share the same center. So you have the spherical shell, which is positively charged, and then there is a gap, and then there is another spherical shell, which is negatively charged, and then the points between any 2 points, the distance between any 2 points within the shell is the same. All right. So let's talk first about the type number 1, which is the parallel plate capacitor. And if you recall, we have calculated, using Gauss's law, we have calculated the electric field due to a sheet, a sheet carrying some surface charge. For example, here positive surface charge we found it to be E is equal to sigma, the surface charge, divided by 2 epsilon naught. Now in the parallel plate capacitor, we have a positive plate, which is going to give me the electric field on this side, the left, and the electric field on the right hand side, sigma over 2 epsilon along the direction of I, and the electric field here is along the direction of minus I. And the positive plate will give me the same, except it's the electric field on the left will be I hat, along the I hat, and the right region will be along the negative I hat. So when I put my two plates together, so this is my negative plate and this is my positive plate, you see that the electric field in this region and the electric field in this region, they're both equal to 0. Because if you add this to that, that's going to give you 0, and if you add this to that, that will give you 0 here. However, the electric field in between the plates is equal to, this is in between, not right, this is in between the plates. Let me get the pen. So this is the electric field in between the plates is equal to sigma, as you see here, the electric field between the plates is sigma over epsilon, and therefore delta V, which we defined, or we found out a few minutes ago, that it's equal to E multiplied by the gap in between these two plates, which is D, is simply equal to, remember, sigma is simply this sigma here, this is Q over D, this is sigma. Okay, so this will be sigma over epsilon D, and that's what the electric potential difference between the two plates. All right, so we experimentally know that Q is proportional to V, and the constant of proportionality is C. So if I set my V is equal to if I set my V here is equal to Q over C, that's my first formula. And then if I go back to the previous slide where I have found that V, I'm taking V infinity is equal to 0. So just so that I get V, right? If I do that, then if I compare these two equations, or these two terms here, if I compare these two, then from here I find the Q's will cancel. Okay, and I get 1 over C is equal to D over epsilon A, or C is equal to, so as you can see, the capacitance, C is the capacitance of this parallel plate capacitor, which has a uniform electric field. As you can see, it's uniform in this region, and it's when you get to the edges, it's not as uniform. So one thing that you should notice, that the capacitance, it depends on A, and inversely proportional D. A is the surface area of the plate, which is the same for both of them, and D is the distance between them, or the gap, and epsilon naught describes the medium in between them. So what we say here, we say that the capacitance is a purely geometric value, and it's constant. Once you build your capacitor, then the capacitance of that capacitor is constant. So if we take a very quick example, which we've done in class, if I take two opposite, and now remember I have the, they're separated by, what is this? They're separated by a gap of 5.33 millimeters, and there is a potential difference of 600 volts exists between the plates. He wants to know, find the magnitude of the electric field. Well, we can say delta V is equal to ED, and you can, from here you can find E. And the magnitude of the force, we know that F is equal to QE. So from here I can, Q is, this is electron, so it's, the electron is 1.6 times 10 to the minus 19 if I want the magnitude. And if I want the direction, of course, of the force, would be opposite to the electric field. All right. So calculate the speed of a proton. There's another example that we've done in class, and I'm just gonna show you very quickly now. Since delta V is equal to the work divided by Q is the charge, then work is equal to the change in kinetic energy, and assuming that the proton started from rest to some final speed V, so I can, from here, I can calculate the final speed of the electron, which is found to be 1.52 times 10 to the power of 5 meters per second. All right, another point that we discussed in class, or actually I should point that out here again, is that once you have your plates set, so this is my positive plate and this is my negative plate of the parallel plate capacitor, and there is an electric field, uniform electric field in between, then the voltage, there will be a voltage difference as you go across along the electric field. So as you go across from point, let me see, from point 1, 2 to 4, 1, 2, 4. So here the potential difference at here, this is my high potential, which is 50, and then it starts to decrease and get to lowest potential possible, which is 0. And then when you go across this way, along the vertical, you experience a potential difference. So going from 1 to 2, you experience a potential difference. From 2 to 3, you experience no potential difference. So delta V between 2 and 3 is 0, and 3 to 4 there is potential difference, 2 to 4 there is potential difference, 1 to 4 there is potential difference. What the idea here is that if there is a potential difference, that means the electron or the charge is actually experiences, or it will move across. So it will move, and it will work will be done in moving this charge from 1 to 2, or from 1 to 3, or from 3 to 4, or 2 to 4, etc., etc., etc. Again, we went through this in detail in class. So you know, delta V can be calculated between 1 to 2 and 2 to 3 is 0. So the charge, if you go from 2 to 3, does not change. The voltage does not change. There are the same height or the same potential. Okay, and this is usually called the equipotential lines, which we covered in the previous chapter. Another point that you should, this is similar to what I was just saying, that if you go from point A to point B, now if you take this path, of course, then you're going to experience some change in potential. However, if you go from point A to C, if you go from point A to C, which is along the direction of the field, you will experience a potential difference. But if you go from B to C, which is perpendicular to the field, you will experience no potential difference. So if you wanted to calculate the work will be 0, because the force will be either this way or this way, depending on the charge, depending on the sign of the charge, and the motion is this way, so the angle is 90 and cosine 90 is 0. So what we say here, no work is done as the charge moves perpendicular to the electric field. And so that's what we're saying here, that if a charge moves perpendicular to the electric field, there will be no work, and thus there will be no potential or no difference in the potential. The potential difference will be equal to 0. Okay, the second type, which is the spherical plate capacitor, actually the third type, we need to calculate the capacitance. In order to calculate the capacitance, we first need, okay, this is my positive charge, and this is my negative charge. Let me get the pen here. So this is my positive charge, negative charge, and this is my positive charge, and this is my capacitor here. The space in between them is the space where the electric field is uniform. So that means what? It means if I take this point, and if I take this point here, they have the same electric field. The magnitude of the electric field in these 2 points is the same. Similarly at this point, similarly at this point. So if I pick a point anywhere along this Gaussian surface, then the electric field should be uniform in this aspect. The direction, of course, would be different. So anyway, so we have calculated the electric field to be, or we've used Gauss's law to calculate the electric field many times using Gauss's law. And this is the electric field in this region here. So in order to calculate delta V, we use this formula, okay, which again we covered last chapter. And if you put the electric field here, if you put it here and then you integrate, you find you're integrating 1 over, or dr over r squared, which is simply 1 over r, and then you take the limits from a to b, the limits from a to b minus 1 over r, I should say, and then that will give you the delta V is equal to that. Now remember, Q is equal to, as always, C multiplied by V. So that means when I do that, I have Q, I have V. If I get C, which is equal to Q over V, then I get my capacitance for the spherical plate capacitor. And again, as you can see, it depends only on the dimensions, A and B, A being the radius of the inner electrode, or the positive electrode, and B being the radius of the inner region, or the inner part, or the inner surface of the outer shell. Okay, and of course epsilon is the region, or defines the space in between them. In this case it's vacuum, and the 4 pi is constant that's coming from Gauss's law. All right, let's talk about the cylindrical one. The cylindrical one, we have 2 cylinders, concentric again. This is one radius is A, and this the outer one, the inner side of the outer one is B. And again, we've used Gauss's law to calculate the electric field. And that was our electric field from Gauss's law. That's in this space here. So this is the electric field in this region here. All right. So again, if I want delta V, I use this formula, or this expression, and from there I find, after you integrate 1 over r, which gives you the natural logarithm of r from a to b, and then you do all the integration, and this is V. Again, you use Q is equal to C V, and then if you do that, that's your if you do that, I think we've done that in class well, then you get the capacitance for the cylindrical plate capacitor. Again, it depends on the dimensions, which this is L, and it depends on B and A, which again are the dimensions of the inner and the outer, or the 2 radii of the 2 cylindrical shells. Again, it's a geometry, depends on geometry and epsilon. All right. So with this, the second point we wanted to look at is the parallel and series combination of capacitors. So we've seen that, and remember, if we set the capacitance, or the capacitor, and then what we wanted to do, we wanted to be able to manipulate the value of this C, because once I said, I think I said at the beginning of the lecture, is that once you build the capacitor, it's the constant value. So what happens if I'm interested in increasing the capacitance or decreasing the capacitance within the circuit, within the device? So what I do, I use what's so-called the series and parallel combination of capacitors. So in the series combination, so it's simply the 2 capacitors are joined in this way, where positive negative, positive negative, so the negative is connected to the positive and the negative is connected to the positive through the source. So the equivalent capacitor will be this way. However, or not however, but on the other hand, the parallel plate capacitor or the parallel combination, you have the two capacitors are connected in such a way that you have the negative is connected to the negative and the positive is connected to the positive sides, and the equivalent capacitor, as we'll see in a minute, it will be a combination of the two. What we want to do next, we want to find the equivalent capacitor if I have, for example, a parallel series combination, and in a few minutes what happens in a parallel combination. So in series, where the capacitors are connected this way, positive, negative, positive, negative, positive, negative, first of all, they all have the same charge. So the capacitors here, all three capacitors, when they are connected in series, they have the same charge, Q, Q, Q. Right? And the potential is divided among them. So the potential will be this potential here, the potential difference will be equal to the sum of V1 plus V2 plus V3, and the sum of the individual, of course, the individual voltages will equal to the power source, which I mentioned in a few minutes, ago. So the total potential is defined as V1 plus V2 plus V3 in this case, and V is equal to QC, or Q is equal to VC. Okay, and so the Q total over C total, or Q equivalent over C equivalent, will be Q1 over C1 plus Q2 over C2 over 3. But remember, these guys are the same according to this comment here. So that means this will cancel, or these three will cancel, and then I have 1 over C equivalent is the sum over 1 over C1 plus 1 over C2 plus 1 over C3, and that's what the summation. What this summation here is referring to. In the parallel combination, what we have the voltage is the same. So V across each one of the, so V here is the same as this V, is the same as this V, and that's understandable because it's connected to the same terminals in both sides. So we can utilize that, however, the charge is not the same. So in series, the charge is the same, but the voltage is not. Here, the voltage is the same, but the charge is not. So if we do this, and then we say, okay, Q is equal to CV, C equivalent, V equivalent, or total, is equal to C1, V1, C2, V2. But remember, the V's are the same. So that means this V will cancel with this V, will cancel with this V, will cancel with this V. And then we have the C in parallel combination is equal to C1 plus C2 plus C3. And that's it. Okay, the second, so this is one way of changing the capacitance, the value of the capacitance inside the circuit. But what if I do not have that leverage or that advantage, and I wanted to look at, I just have a capacitor and I want to change its capacitance or increase its capacitance? One way of doing that is by using something called a dielectric material, by simply inserting a dielectric material in between the plates. So what are the dielectric materials? Dielectric materials are non-conducting materials. So let me just, so they are non-conducting materials, insulators such as rubber, glass, and so forth. When a dielectric material is inserted between the plates of the capacitor, then what happens? The capacitance is increased by a factor of kappa, which is called the dielectric constant of the insulating material. The capacitance increases because the electric field between the plates is decreased. So we have the capacitance in between the plates increases and the electric field is decreased. Okay, so let's see how is that. Now remember, these guys are randomly oriented at the beginning, and when you turn the electric field on, they sort of orient themselves with the electric field, as you may expect. Okay, so when they are not oriented, as you see, the dipole or the sum will give us zero electric field. So again, the orientation of when the electric field here, when they are randomly oriented, the electric field is equal to 0. However, when you turn the electric field on, these guys are oriented, and the result of this is that it will reduce the electric field, as we will see in between the plates, which we'll see in a few seconds. So dielectric constant is a property of the material, or actually it's one of the characteristics of the electric properties of materials. And as you can see here, air has a dielectric constant of 1, paper dielectric constant of 3.7, and glass between 4 and 6, and water is a very high, it is a very high electric kappa, which is equal to 80. All right, so we've seen this before. If I have a parallel plate capacitor, the electric field outside is equal to 0, and the electric field inside is equal to Q over epsilon. And remember, the electric field is proportional to the, the magnitude of the electric field is proportional to the density of the electric field lines. All right, so let's see here what happens when you insert a dielectric between the plates. So we have here plates, the positive and negative plate. We have a uniform electric field. And then all of a sudden, or not all of a sudden, but I introduce a dielectric material in between them while the electric field is on. Now what happens, as you see here, the electric field lines that are, as we have seen before, remember they initiate at a charge and they terminate at a charge. So the electric field lines here, they will be terminated right here, and this one will be terminated right here, and this one will be terminated right here, and this similar to this one. So what's going to happen, some of these lines that I have here will disappear. What does that mean? That means that in this space here, E is reduced. E is gone down, because remember the electric field lines is an indication of the electric field strength, and therefore we say that the since E0 is greater than E0, this is my E0 before I insert the dielectric, and this is E after I insert the dielectric material. So E0 is greater, and kappa. So if I do that, so E is equal to E0 over kappa, or kappa is equal to E0 over E. This means that kappa, the dielectric constant, must always be greater than 1 for dielectric material to work the way we want them. And therefore, the electric field, the new electric field, this new electric field is simply E0. That's my E0, Q over epsilon A divided by kappa. And however, C, the capacitance in between the plates, is now increased by how much? Increased by, so this is my, this is my C0, right? And introduced by, so it's simply kappa multiplied by C0. And therefore the result here is that I was able to increase the capacitance of the capacitor by inserting a dielectric material in between the plates and reducing the electric field for the simple physical situation that we've seen a few seconds ago. Okay, we have two examples which I've looked at in class, but I'll just go over them very quickly. So here I have a capacitance that has this much. So remember, capacitance is measured in farad. There's a capacitance is measured in farad. Q is measured in coulomb, and V is measured in volts. Yeah, so usually we use the microfarad, or the typical numbers for capacitors used in the lab is about in the microfarad region. Okay, so the capacitor is connected to 1.2 volt battery, and then it's charged up. With the capacitor connected to the battery, a slab of dielectric material is inserted between the plates. So I have my capacitor, and it's connected to some battery, which is 1.2 volt, and then I inserted the dielectric material here in between the plates. Okay, and what does he want? He wants this kappa here. What's the kappa for the dielectric material that inserted now? Now he told me that as a result there is an increase of the charge. There is an additional charge that we were able to use, which is basically you can introduce more charge because the electric field has gone down. Okay, now how will we do that? Now he told me, now let's start with the famous formula, Q is equal to CV. I know C0 is equal to 1.2. He gave me that. That's before inserting the dielectric, and I know V is equal to 1.2. And remember, V is not going to change. The voltage here, 1.2, is not going to change. but then he told me that there is a change, an additional charge. So that means Q minus Q0, that's delta Q, which is this number here, 2.6, is equal to what? Is equal to Q is, remember, Q is equal to CV. So it's equal to CV, Q is equal to K or kappa, C0V, that's the new charge. Okay, and C0V is the initial one. So if I take this out, then I get C0V multiplied by kappa minus 1, kappa minus 1, and that's the solution for my, and from here I can, delta Q is given, and C0 is given, C0, and V is given, and from here I can find kappa. A parallel plate capacitor has a capacitance of kappa when filled with dielectric. The area of the plate is kappa, the separation between the plates kappa. What's the dielectric constant? So in here, what do I have to do? I first have to find C, which is simply what? Epsilon A divided by D. I have A, I have D, and epsilon, of course, is known, so I can find C. Okay, and what's the dielectric constant? Okay, so the separation between the plates, and then from there I can find the kappa, between the or kappa for the oh no, this is kappa. This is the C after inserting the dielectric. So this will be equal to kappa multiplied by epsilon multiplied by the area divided by D, and from there I can find the dielectric constant. Okay. The second thing, remember what we started with. We started with the idea that we want to know, or we said that this capacitor is a device, an electronic device, a passive electronic device that's used to store energy. So now is the time to know what is that energy stored in that capacitor, on the capacitor is. In fact, we can find that by simply looking at the graph of voltage versus Q, which we know it's a linear, it has a linear behavior. So if you look at the area under the curve, which is half Q, V times Q, okay, half the rise or half the height times the base, okay, and if you think about that, this is V is in voltage, okay, and Q, the voltage, which is joules per coulomb, and Q is in coulomb. So you see that the coulomb will cancel with the coulomb, and the area is actually measured in joules, and that's the energy. So the energy, I've added these two. So the energy the energy stored in a capacitor is actually equal to half QV. The energy stored in a capacitor is equal to a half QV, which we checked it from the units. Now I've added these two formula, which we did not, they're not really required, but this is basically the force needed to take the plates, if you have a parallel plate capacitor and you want to take the plates apart, this is the amount of force needed to take the plates apart. And this is the work needed to do that. Okay, so that is something that you may want to look at, but we're not too much worried about that. Okay, all right. So the potential energy of a capacitor, we can write this. So this is the one we just derived. And using C is equal to Q over V, we can have three different forms of it. We can have the potential energy stored in a capacitor half CV squared, or the potential energy stored in a capacitor Q squared over 2C, or half Q squared over 2C, whichever you wanted to use, whichever formula you wanted to use, depending on what you're given in the equation. So this energy is referred to as the potential energy stored inside a capacitor. And remember, the slope of VQ, this is important here, the slope, okay, the slope, this slope here, which is simply what? V over Q. That gives me 1 over C. Okay, so the slope is Q, V in this case over Q. That gives me the the inverse of C, or Q is equal, as you can see, Q is equal to CV. All right. And another thing that we need to look at is something called the energy density. The energy density is simply the energy divided by the volume. if you look here, the energy which we found from here is equal to what is it, CV from this equation here. So the energy is equal to that. Now I know V is equal to, I can do a little bit. So if I replace C with this value, so that's C, and then V is equal to ED, which we had before, so that would be E squared D squared. So what does that mean? That means a half E squared from here, and then I have AD. Remember, one of the D's will cancel with this one, okay? So I have the energy, the potential energy also can be defined in terms of the electric field between the plates, the area of the plates, and the separation between the plates in this form. But what is AD? AD is simply the volume between, this is A, the surface area, and D is the separation. So this gives me the volume in the region between the plates. If I divide by that, if I divide this U divided by the volume, I get what's called the energy density, or the energy per unit volume. So this is the energy per unit volume within the capacitor. All right? Okay. So let's summarize, and then we'll break. We'll finish this, and then we'll go to part 2, where we take the examples and the questions. So summary. Experiments show that the amount of charge Q stored in a capacitor is linearly dependent or linearly proportional to the electric potential. Q is equal to C delta V. Okay, and I'm taking the absolute value. If you want to take one of the V's to be 0 at infinity, then that will be simply Q is equal to CV for simplicity. For the parallel plate, so C, and so that's the first thing that we did. And then next, we looked at the capacitance for 3 types of capacitors. So we have the parallel plate capacitor, we have the cylindrical capacitor, and we have the spherical capacitor. And as you can see, in all 3 of them, the capacitance C is depends on the geometry, or basically the area, the dimensions, area and D. Here B and A, and L is the length of the cylinder. A is the radius of the inner sphere, and B is the radius of the inner side of the external shell, and so it depends on the it depends on the dimensions. After that, we looked at the combination of capacitors. So in the parallel capacitor combination of capacitors, we have C equivalent is equal to C1, C2, C3 plus. And if it is series, then we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And we also talked about the potential energy stored in a capacitor, which we found it to be either a half QV or a half QV or a half C delta V squared, or Q squared over 2C. And then we found the energy density, which is basically the potential energy per unit volume in the space between the plates of the capacitor. And then we said that if you insert a dielectric between the 2 plates, what do you get? You get an increase in the capacitance, an increase in the capacitance by kappa. So nu C will be equal to kappa times C, and kappa is greater than 1. It has no units. I forgot to mention that this kappa has no units. So C is equal to, or C nu is equal to kappa times C 0. And this is a summary. This is all we have taken. If you sort of comprehend this slide and understand it, then the rest is just application. So I'll stop here, and then the next, or part 2, we'll just look at examples and calculations or applications of all of these 3, 4, 5, 6, 7, 8, 9, 10 formula. All right, see you in a bit.